Hi, this is the continuation from Thursday's lesson. That's Thursday the 8th of October. So we're now on page 11 of the Extension 2 booklet, Complex Numbers, using sums and products of roots to solve problems involving quadratic equations. Now, at the end of last lesson, we looked at the following. If a quadratic equation has real coefficients, in other words, if we're looking at ax squared plus bx plus c equals 0, and if the coefficients a, b and c are real, meaning that they could be whole numbers, they could be fractions which are rational, or they could be surds. Now they're all real numbers. So if a quadratic equation has real coefficients, and if the discriminant is less than 0, the roots will be complex conjugates of each other. Now, we looked at that at the end of last lesson. Now, because we're also looking at quadratic equations, and if you look back at 2-unit maths, we know that there is a relationship between sums and products of roots that applies to quadratic equations. It also applies to quadratic equations where the discriminant's less than 0 and quadratic equations whose roots are complex. So, same as before, sum of roots is minus b on a, and then product of roots is c on a. So let's just use all of this information in that the roots are complex conjugates of each other. So we're going to use that fact if the coefficients a, b and c are real, and also the fact that sum of roots is minus b on a and product of roots is c on a, with these few examples I'm going to do now. Here is our first example, which is 3 minus 2i is 1 root of x squared plus bx plus c, where b and c are real. You have to find b and c. So first of all, we start off with saying that 3 minus 2i is 1 root, and so therefore 3 plus 2i is the other root, as the coefficients of the quadratic equation are real. So unless you realize that, you won't be able to do anything with this question. So it's really important to look at the coefficients. They're real. So because 3 minus 2i is 1 root, then the complex conjugate 3 plus 2i is the other root. So now we can just do sum of roots. Now we know that sum of roots is minus b on a. So the sum of your two roots are 3 minus 2i, plus your other root is 3 plus 2i, and that equals minus b on a, which happens to be, now we'll just simplify this on the next row. So we've got 3 plus 3 is 6, so therefore 6 minus 2i plus 2i is 0. So over here, our minus, now your b happens to be b and your a is 1. So therefore we've got negative b is 6, or we've got that b is negative 6. And so we've found b. So now we look at product of roots. So we know that product of roots is c on a. Now our two roots are 3 minus 2i times 3 plus 2i, and the product of those roots is c on a. Just expanding that and substituting for c and a. This is in the form a minus b, a plus b, so it's just going to be difference of 2 squares. So we've got that it's 3 squared minus 2i squared equals, now c here is c, and a is 1. So therefore we've got that 9 minus 4i squared equals c. Now we know that minus 4i squared is plus 4. So we've got that 9 plus 4 is c. So we've got therefore c is 13. So let's have a look. So therefore we can say that b is negative 6 and c is 13. Now what I'm going to do, you don't have to do this normally, but I'm just going to show you how this works. So let's just check our answer. So checking our answer, we know that b is negative 6 and c is 13. Let's just have a look. X squared minus 6x plus 13 equals 0 is my equation. If I just look at what my roots are by doing the quadratic formula, or I could complete the square, I'm going to do quadratic formula. So it's negative 6. So it's 6 plus or minus the square root of b squared is 36 minus 4 times 1 times 13 is 52 over 2 times 1 is 2. So we get that the roots are 6 plus or minus the square root of negative 16 over 2, which is 6 plus or minus the square root of 16i squared on 2, which happens to be 6 plus or minus 4i on 2, which is 3 plus or minus 2i, because it's 6 divided by 2 is 3, 4i divided by 2, sorry, just off the screen, is 2i. Notice that our roots are 3 plus 2i, 3 minus 2i, so we know definitely that our answer of b equals negative 6 and c equals 13 is correct. Now, you don't have to do that in a question. It's just so that I can show you that it is correct. Now we can look at examples 2 and 3. So firstly, example 2, x squared plus 6x plus k equals 0 has one root alpha where the imaginary part of alpha is equal to 2. Now, if k, this k here is real, find both roots of the equation and find the value of k. Now, before we start, remember, we're going to use sum and product of roots if we can. So let one root of the equation be alpha, which is x plus yi. Now, we know that the imaginary part of alpha, so our root is alpha, it's got an imaginary part, so we know it's a complex number, x plus yi. So we know that the imaginary part of alpha is 2, so your root is x plus 2i. Okay, now, so therefore, the other root will be x minus 2i as the coefficients, so as the coefficients of your quadratic equation are real. Okay? Now, let's look at sum of roots. So if we look at sum of roots, we know that that is x plus 2i plus x minus 2i. I really don't need brackets here, but I've just written them now, is minus b on a. Let's add and do our substitutions. So we've got x plus x is 2x, 2i minus 2i is 0, equals minus b on a. Now b is 6, so it's negative 6 over a is 1. So we've got 2x is negative 6, and so therefore x is negative 3. So we've just found what x is. Now that helps us because therefore our roots are negative 3 plus 2i, negative 3 minus 2i. So that will help me continue with my question. So now I can do product of roots. So the product of roots we know is negative 3 plus 2i times negative 3 minus 2i, and we know that product of roots for a quadratic is c on a. Now this is a difference of two squares because it's in the format of a plus b, a minus b. So we get that it's negative 3 squared minus 2i squared equals, c is the value k and a is a 1. So we've got 9 minus 4i squared is k. So therefore k is 9 plus 4, which equals 13. So therefore we've found both the roots of the equation. Sorry, we're just having some focusing problems. So therefore the roots of your equation are minus 3 plus 2i minus 3 minus 2i. So we've found both roots and we've found that the value of k is 13. And that's the end of that question. So now let's look at example 3. In example 3, you're asked to find the quadratic equation with roots 1 plus i and 1 minus i. Now I'm going to do this two different ways. So I'll do one way over here, and I'll do the other way over there. Now, normally, for example, if you knew the roots of your quadratic equation and they were 2, let's say 2 and 3, you'd write that your quadratic equation is x minus 2 bracket x minus 3 equals 0. So what we're going to do is the same thing with this. If these are my roots, then therefore my quadratic equation is x minus the first root times x minus the second root equals 0. So now I need to expand that. Okay, so I get x squared minus x bracket 1 minus I minus x bracket 1 plus I, and then we get plus 1 plus I times 1 minus I. So we're multiplying the last two there. Sorry, equals 0. I just need to get more room there. Expanding, I get x squared minus x plus xi minus x minus xi. And here I've got a difference of 2 squares, so I'll get plus 1 minus I squared equals 0. So simplifying furthermore, these cancel, and I get x squared, well, I've got minus x, which is minus 2x. I've got plus 1, and this is also plus 1, minus I squared is plus 1, so I get plus 2 equals 0. Okay, and so that's my quadratic equation with roots 1 plus I, 1 minus I. Now, another way that you can do this is as follows. You can look at sum of the roots. Now we know sum of roots is minus b on a. Now, sorry, before I write that, I can do that, which happens to be 1 plus I plus 1 minus I. In other words, minus b on a is equal to 2. So we'll just leave that there. And so the product of roots we know is c on a, which is 1 plus I times 1 minus I. Now that's a difference of 2 squares, so we get that c on a is equal to 1 minus I squared. In other words, it's 1 plus 1. In other words, c on a is 2. I'll just move that down. Okay, so c on a is 2. Now, we know that ax squared plus bx plus c equals 0 is the general form of a quadratic equation. Now, if we divide through by a, we get x squared on, in other words, it's the same as dividing through by a, I get x squared plus b on ax plus c on a equals 0. So I just need a bit more room here. I'm just going to wipe that out. And so now substituting from there, so therefore my quadratic equation is x squared. Now b on a, we know that minus b on a is 2, so therefore b on a is negative 2. So I get minus 2x, and we know that c on a is 2, plus 2 equals 0. So therefore, that's my quadratic equation. So my quadratic equation is that. X squared minus 2x plus 2 equals 0. Notice that it's the same as what I got over here. So either method for example 3 is acceptable. Okay, we're going to go to page 12 now. In this next part, we're finding the square roots of a complex number. Now, if you're trying to find the square roots of 3 plus 4i, for example, so you're trying to find the square root of 3 plus 4i, what we're doing, if we just look up here, to find the square root of a complex number, a plus bi, we will use the following. We'll let z squared equal a plus bi, and so therefore, taking the square root of both sides, we'll therefore get that z is the square root of a plus bi. Okay? So, the method that we will use is we will let z equal x plus yi. We'll then evaluate x plus yi squared, and then we will equate it with the a plus bi. And to do that, we will equate real and imaginary parts for both those z squared expressions that we come up with. So look, this is going to take a fair bit of room. We're going to need 2 columns again. Okay, so we will start by let z squared equal 3 plus 4i. Okay, so, and we'll also let z equal x plus yi. And so therefore z squared is x plus yi squared, which happens to be x squared plus 2xyi plus y squared I squared. In other words, z squared is equal to, now this is x squared plus y squared times -1, so it will be x squared minus y squared plus 2xyi. Now, I'll just call this equation 1 and equation 2. Now, equating, see how we've got two expressions for z squared? We've let z squared equal 3 plus 4i because we're trying to find the square roots of, we're trying to find the square root of 3 plus 4i. So if we let z equal the square root of 3 plus 4i, then we can see that z squared is 3 plus 4i. Okay, that's why we've done this. Okay, so we're trying to work out what z is. That's what we're trying to do. Z will be the square root of 3 plus 4i, but to start this question, we'll say, well, therefore we start with z squared is 3 plus 4i. We also know that z is x plus yi, so we come up with an expression for z squared. And so we equate, now we've got two expressions for z squared. So equating real and imaginary parts, so real and imaginary parts in 1 and 2, we can see that the real bit here is x squared minus y squared, and that must equal the real part there, which is 3. So we get that x squared minus y squared is equal to 3. I'll call this equation 3. And we will get that this 2xy bit, the coefficient of the I here, equals the coefficient of the I there, which is 4. So then we get 2xy equals 4. Now, just rearranging that, I get that y equals, I'll call that equation 4. I get that y equals 4 over 2x, which is 2 over x. Okay? So now what I'm going to do, we see what we're doing here is we're solving these two simultaneously. We've got the x squared minus y squared is 3, call that equation 3. 2xy equals 4, that's equation 4. I want to solve these two simultaneously because we've got two unknowns and you need two equations. So making y the subject here and then substituting in there. So then we're getting that y equals 2 over x, and we'll sub into 3. And we will get that x squared minus 2 over x squared equals 3. Now, we need to expand. And so I'll just leave that up there too. And we've got x squared minus 4 over x squared equals 3. And so multiplying through by x squared, we get x to the power of 4 minus 4 equals 3x squared. So we're multiplying through by x squared. Taking everything to the left-hand side, we've got x to the power of 4 minus 3x squared minus 4 equals 0. We now factorize this. We'll have an x squared there and an x squared there. The factors of -4 that add up to -3 would be -4 and plus 1. And so therefore we get that x squared equals 4. In other words, x equals plus or minus 2. Or we get that x squared equals -1. Now that has no real solutions for x. Now, the reason x has to be real is that our complex number, x is made up of x plus yi, where x and y are both real. So we now have two possible values for x for this complex number here. So when x equals positive 2, we need to see what y is. We're going to sub into this equation here. We get that y is 2 over 2. So we get y will be 1 because it's 2 over 2, which is 1. And also when x is -2, we get that y is 2 over -2, which is -1. And so therefore, we can write down what our complex numbers are. And so therefore, z is equal to x plus yi, And in this case, it's 2 plus 1i, or 2 plus I, and, or z equals -2, that's the value of x there, minus I. So therefore, we can say that the square roots of 3 plus 4i are 2 plus I and -2 minus I. So they're my square roots of 3 plus 4i, okay? Because see, z is the square root of 3 plus 4i. Z happens to be x plus yi, but to do this question, you need to work with z squared, okay? So we're going to do a question that's the same, just different numbers. Can you please use that method? Notice it's going to take up a bit of room, all right? So you can pause the video, try it yourself. You want to find the square roots of 5 minus 12i. Restart the video when you are ready. Okay, once again, we let z equal x plus yi, and z squared equals 5 minus 12i. So therefore z squared here is x plus yi all squared, which is x squared plus 2xyi plus y squared I squared, which is x squared minus y squared plus 2xyi. Now we can say equating. You don't have to call them equations 1 and 2 if you don't want to. So equating real and imaginary parts of z squared, you could just write that. You would get that x squared minus y squared equals 5. And we can call that equation 1 now. And we've got that 2xy is equal to -12. Call that equation 2. Rearranging that, we get that y is -12 on 2x, which happens to be -6 on x. Now we're going to sub that into equation 1, and you'll get that x squared minus -6 on x squared equals 5. And we keep going. So therefore x squared minus 36 on x squared is 5. Multiplying through by x squared, we get that x to the 4 minus 36 equals 5x squared. Bringing the 5x squared over, you get that equal to 0. X to the power of 4 minus 5x squared minus 36 equals 0. Now we can factorize. X squared minus 9 times x squared plus 4 equals 0. And so therefore x squared is 9, or x squared is -4. That has no real solutions for x. And here we've got that x is plus or minus 3. So now, when x equals +3, you need to work out what y is, and it will be -6 on 3, which is -2. And when x is -3, y is -6 over -3, which is +2. And so therefore, the square roots of 5 minus 12i will be your x plus yi. So we get 3, just looking here, 3 minus 2i, and -3 plus 2i. Okay? All right, now we can try the last question to find the square roots of -6i. Okay, hopefully you've tried this, pause the video, and it's exactly the same method as the 2 questions before. I'll just quickly go through it. Again, let z equal x plus yi and z squared equal to -6i. We work out our expression for z squared, which you know that you will get x squared plus 2xyi plus y squared I squared, which is x squared minus y squared plus 2xyi. again equating real and imaginary parts of z squared, you will get that x squared minus y squared. Now, z squared is minus 6i, which really is 0 minus 6i. So therefore, x squared minus y squared is 0. That's equation 1. And your second equation will be that 2xy equals negative 6. In other words, y is negative 6 on 2x, which happens to be negative 3 on x. Okay, you don't want to make a careless error there. Just be very careful when you do that. Substitute into equation 1. We'll just keep that separate. And you will get that x squared minus negative 3 on x squared is 0. Notice I'm using my brackets, putting this in brackets as well, and squaring it. So I've got x squared minus 9 over x squared is 0. Multiplying through by x squared, we get x to the power of 4 minus 9 equals 0. So therefore, this is a difference of 2 squares. It's really x squared minus 3 squared is 0. Sorry, x squared squared minus 3 squared is 0. So therefore, you've got x squared minus 3, x squared plus 3 is 0. And so we get that x squared is 3 or x squared is negative 3. This has no real solutions. So therefore your solutions are x equals plus or minus the square root of 3. Now we need to work out our y values. Okay, so when x equals positive root 3, just substituting over here. Sorry, now we can't see it. I'll just make it a little bit wider. So when x is positive root 3, we get that y is negative 3 on root 3. Now just think of 3 as root 3 squared, or you can just rationalize it, and if you rationalize it, you'll get negative root 3. Okay, and also when x is negative root 3 here, we get that y is over here negative 3 over negative root 3, which is a negative divided by negative is a positive, and we get positive root 3 if we rationalize that. So therefore, the square roots of negative 6i will be x plus yi, which happen to be when we get root 3, that's your x plus yi, so we get minus root 3i, and we also get negative root 3 plus root 3i. Okay, so we're just substituting in the x plus yi values that we get up here. So we get root 3 minus root 3i, negative root 3 plus root 3i. Okay, sorry, that's just a bit off the screen. So that's the end of page 12. Okay, we'll go to page 13. Okay, in our next page, page 13, we're looking at finding the cube roots of a number. Now, first what we're doing, we're going to express z cubed plus 64 as the product of 3 linear factors. Hence, we want to find the 3 cube roots of negative 64. Okay, let's just do what they're asking first. So we're expressing z cubed plus 64 as the product of 3 linear factors. Now this really is z cubed plus 4 cubed. Now in the 2-unit course, you've learned how to factorize sums and differences of cubes. Now that is the factorization for this. So the factorization for a cubed plus b cubed, if you remember, is a plus b times a squared minus ab plus b squared. Just be careful, don't put a 2 here. This factorization only has one minus in it. The a cubed plus b cubed has the plus here first, and then in the next available spot is the minus. So using this rule that you've learnt from 2-unit, we get z plus 4, then we get z squared minus 4z plus 4 squared, which happens to be 16. Now, we haven't got 3 linear factors here. We've got one linear factor because that's just a normal z, so that's linear, but this is a quadratic factor here because it's z squared. So we need to factorize this z squared minus 4z plus 16. Now if we look at that, there is, and you try and look for two numbers that multiply to give 16 but add up to give -4, you can't find two numbers that multiply to give 16 and add up to give -4. So what we're going to do, we're going to complete the square on this. Okay, so we've got here still the z plus 4. Be careful here that your z's don't look like 2's because we're going to come up with 2's in a minute. And I want to complete the square on z squared minus 4z plus 16. So I get z squared minus 4z. Now, I need to complete the square here, so adding and subtracting at the same time. Plus half the b is 2, so we get plus 2 squared minus 2 squared, so we've added it on and taken it away straight away, plus 16. And we get, again, z plus 4. Then we've got, just might put these little lines through the z's so that you know that they're z's, okay? So just got these little lines through the z's. And we've got z squared, sorry, not z squared. See here, we've got a perfect square, so we've got z minus 2 squared. Now I need another bracket here. And then I've got, so I've taken that, done that bit. This is z minus 2 squared. Then we've got minus 4 plus 16 is plus 12. Now, we still need to factorize this. Now, this is a sum of two. Look, I can write 12 as the square root of 12. You can write any number. Sorry, I can write 12 as the square root of 12 squared. So you can really write any number as a squared number. So we're just going to keep going. So we've got z plus 4 times z minus 2 squared plus, sorry, not plus. I want to actually write this as a difference of 2 squared so I can factorize it. So I've got minus 12i squared. Now, 12i squared doesn't look like it's a square number, so I'm going to now make it look like a square number. Then I've got z minus 2 squared. Now I'm going to write this as minus root 12i squared. So now I've got difference of two squares here. I've got a squared minus b squared. So root 12 squared is 12, I squared is I squared. So now I can factorize this. And I've got z plus 4. And this is in the format, we know, of a squared minus b squared, we know is a minus b times a plus b. So I'm factorizing this, okay? So I've got a, this is my a, minus, this is my b, times, that's z, a plus b. Now, root 12 can be written as root 4 times root 3, which is 2 root 3i. So let's do that. So z plus 4. Then we've got z minus 2 root 3i. And z minus 2 plus 2 root 3i. Now, if I want, so there I've written it with as 3 linear factors. The other thing I can do here is z plus 4, z minus, and in brackets I've got 2 plus 2 root 3i. And here writing it as minus z minus 2 root 3i. Okay, but look, this form up here is perfectly fine. Okay, so now we've expressed z cubed plus 64 as the product of 3 linear factors, hence find the cubed roots of 64. So if we let z cubed plus 64 equal 0, then z cubed equals negative 64. So therefore z is the cubed root of negative 64. So therefore, because we've found the 3 linear factors of z cubed plus 64, therefore the cubed roots of 64 are, be careful here, actually I want to rewrite this bit here, so just coming back up here, I've got z plus 4, but I'm going to write it as z minus negative 4, so therefore, actually I can just leave it like that. sorry, I'll just go back. Don't need to do that. So I've got z plus 4. So now putting that, if we put that all equal to 0 up here, we would get that z is negative 4, and z minus that, to make that 0, I'd have to have the identical thing as that, 2 plus 2 root 3i, and z minus this, my other root is 2 minus 2 root 3i. Okay, so therefore these are the cube roots. So therefore the cube roots of negative 64 are the following. So z is the cube root of negative 64, and we can see here if we put that all equal to 0, then z would be negative 4, 2 plus 2 root 3i, 2 minus 2 root 3i. Okay, now we're going to do the same thing with the next example. Okay, here is example 2. And in example 2 it says to express z cubed minus 1 as the product of 3 linear factors. Now we're going to do exactly what we did up in example 1. So if you want, you can try it on your own, pause the video and restart when you're ready. Okay, so z cubed minus 1 really is z cubed minus 1 cubed. And if you factorize that, now this time we've got a cubed minus b cubed, and from the 2-unit course we know that this is a minus b, a squared plus ab plus b squared. Now this almost looks like a perfect square except for the 2. Notice with the a cubed minus b cubed, you got the minus here first, and these are all pluses because in each of these factorizations there's only one minus. So this has got the minus here, so therefore no minuses there. So if you factorize this, you get z minus 1, and then we get z squared plus 1z, which is just z plus 1. Now we need to, here I've got one linear factor and a quadratic factor. So I need 3 linear factors, so I have to factorize this. Now to factorize this, I'm going to complete the square. So I've got z minus 1. Now z squared plus z. Now the coefficient of the z here is 1. So half of that, half of 1 is a half. So plus a half squared minus a half squared, and then add that 1 on at the end that was there. Okay, so now we can write it as a perfect square here. The video there, I'm just restarting. So we've got z minus 1, then these first 3 terms make the perfect square z plus a half squared. Then we've got minus a half squared, which is minus a quarter, plus 1, which would be plus 3/4. Now we can write that as z minus 1, z plus a half squared minus 3/4 I squared. Okay, because I squared is negative 1, and so therefore that's the same, plus 3/4 is the same as minus 3/4 I squared. Now I need to write that 3/4 I squared as a square number, so it would be root 3 on 2 I squared. I'll just make square brackets here actually. Okay, so therefore this is in the format of a squared minus b squared. So therefore I can factorize it, and it's z minus 1, z plus a half minus root 3 on 2i, and z plus a half plus root 3 on 2i. Now I'm going to write that in the format of z minus z minus. So therefore that's z minus 1, z minus negative a half plus root 3 over 2i. Reason I'm doing this, it helps with the next step. Z minus negative a half minus root 3 on 2i. Okay, so this is where you would stop, where you express z cubed minus 1 as the product of 3 linear factors. But I'm doing this next step here because it's going to help me when I find the 3 cube roots of 1. So if z cubed minus 1, if we let it equal to 0, then z cubed equals 1. And so therefore z would be the cubed root of 1. So far, whenever you've looked at cubed root of 1, we've only written that our answer is 1. But if you've got z cubed equals 1, that is a cubic. So there must be 3 solutions. It just happens that one of the solutions is real and the other two solutions of the cubic are complex solutions. So we've only ever written real solutions, okay, in 2-unit maths, but now you will write all solutions, complex and real solutions. So therefore, looking up here, if you put this equal to 0, because if we're putting z cubed minus 1 equal to 0, because we're trying to find, we're taking this over and we're getting, well, z cubed is 1, therefore z is the cubed root of 1. So therefore, putting that equal to 0, we get that z is 1. Because we've written it in this format, z will be identical to this. We get minus a half plus root 3 on 2i, and the other root is negative a half minus root 3 on 2i. Okay, now, another thing I want to say, and I'm going to go up to the other question as well. Z cubed minus 1 is a cubic, and it has real coefficients. Because the coefficients of this are real, notice that two of the roots are complex conjugates of each other. Notice that. Also, up in this example here, z cubed plus 64, this is 1z cubed plus 0z squared plus 0z plus 64. The coefficients of all your terms are real, and so therefore two of the roots are complex conjugates of each other. 2 plus 2 root 3i, 2 minus 2 root 3i. Okay, so just keep that in mind if you're asked questions. We will do that in the polynomials topic, which is next term, where you're asked to factorize expressions, cubics, for example. Okay, that's the end of page 13. Look, I'm going to stop this video now because it's getting quite long. In the next video, we'll be looking at pages 14 and 15.